Today, I'd like for you to meet my nemesis. This snake, of course, represents many metaphorical things, such as Python and the concept of betrayal. Despite that, this is actually a very friendly snake, but for the purposes of this video, it has agreed to wear this badge, dictating that it is in fact my nemesis. Now, because this snake represents, in addition to Python, the general concept of betrayal, this snake is very good at the game rock, paper, scissors. But because the snake is a computer program and there's nothing in this file, we're going to have to build it ourselves. To start with, we'll bring in, yes. We're not going to represent this as a question mark. We're going to represent the bat, which I suppose represents me, as this image. The nice thing is that we can just use emoji in our code like this. Now, there's more subtlety to this, and you can take the word subtlety to mean I'm going to have to replace a lot of characters. We can see here that we've got quite a few things to bring in, don't we? Yes. So the actual choices in rock, paper, scissors are, of course, between statue, newspaper, and importantly for this particular snake, knife. Now we're using Vim mode, so we can type these fast. The problem is that we can't really type them well, because I'm not good at that. Windows, of course, has the ability to copy-paste emoji, but I use a tool called Synergy to sync between my workspaces, and Synergy sure doesn't. It's weird, you know, it's 2025, and people should support Unicode, and sometimes it does. But today, and with this program, it does not. We've, of course, got this data type representing the choices that the user could make, and we have this explicit list. There's another way you can represent this in Python. You can use what's called an enumeration, which would look like class choice of enum. There's no reason not to use an enumeration here. I just prefer to use strings in this case because we mostly use the string representation. So this is, of course, the exact logic that we would use to determine who beats another person. The idea is that if X played paper and Y played rock, that would be a win. If X played scissors and Y played paper, that would also be a win. We could, in theory, replace the payoff matrix with the opposite if we wanted instead for rock to beat paper and paper to beat scissors, but we don't live in the world where that's true. So, of course, we'll be implementing the actual game of rock, paper, scissors, which is necessary in order to play rock, paper, scissors. We'll have a round counter. It starts from 0, even though we're going to visually display it as counting from 1. We're going to have an adversary, which is, of course, the same as our snake. We're going to display information about what round it is every round, and already we have a game that you wouldn't want to play because all it does is make the snake hiss every few milliseconds. What we actually want to do is we want to get a choice from both the player and this adversary that we have yet to define. Note that, while I haven't defined the adversary's behavior, I know what methods it has. So we'll solicit a choice from the player. I'll make this smaller so you can see. The idea is that we have this mapping from things that the player can actually type, because it's hard to type statue, newspaper, or knife. We have this mapping from things the player can actually type to things the player can select. And we'll build that function soon. I just haven't built it yet. And we'll, of course, apply the scoring rules of rock, paper, scissors, which most small children in the US know by heart. But if you're not from the US, you now understand that if both players play the same thing, we'll go 0-0, and otherwise the player who played the winning thing goes 1-0. So that's how the scores relate to each other. You'll occasionally see people score it where people who play the same thing get 0.5. I just like round numbers, so I won't do that. The other thing we'll do is we'll announce how the game played out, because while we now have the scores, the player wouldn't know what they scored unless we display that. We'll be displaying a verb, too, that explains what action was done inside of the round. That's mostly a cosmetic thing. Having done that, our adversary will need to know what actually occurred inside the game, so we'll inform our adversary exactly like that. And that's beautiful. From there, we've got some verbs, exactly as I promised you, and they look like this. And I defy you to come up with a better set of verbs for these 3 nouns. We also, of course, have to give the player the ability to make the choice that we've promised them that they're able to. So this is a little bit dense, but basically we're generating a hint. It'll say exactly RPS, because those are the 3 letters here. We generate a hint. We ask the player to select a character, and we'll uppercase it for them. And then as long as the player's selection isn't a valid option out of the ones that were provided, the player will be asked again. Once the player has responded with an option that was provided, we can actually use that option. Yes. So we'll also provide just a stock implementation of the snake. This is, of course, not how the snake would play if the snake wanted to win, but it is a recognizable opponent. And usually when you're building a program like this, you want to stub things out until you have the real code ready, because the real code is more complicated in this case. Having now done that, we might as well initialize the snake and get to playing. Yes. So now we have here a snake. It's exactly as I described. We can, of course, pick rock. The snake has picked scissors, so we actually win that one. If I pick rock again, the snake picks paper and wins that one. And if I pick rock again, I beat the snake. We can play out a few rounds. Seems like this snake is not going to win the game, which is unfortunate. We can give it a few more rounds to turn it around. Like, oh, the snake's beating us now. So we can actually say that this is a snake that beats me 100% of the time in a single trial. But we wouldn't say that because that's a foolish thing to say, even though there's a lot of research of that quality in the world. We can see that what's actually happened, because we know that this was round 17, is that we had, 6 ties, 5 wins, 6 losses, which would actually imply that our skill level is very close, which would make sense because I'm playing randomly and the snake is playing randomly, and against an opponent who's playing randomly, you can't actually do better than random. So we probably got to make our snake a little bit smarter, because right now our snake would lose to a brick wall or win it to a brick wall. It doesn't really matter. There's a standard approach to playing games of this type really, really well. And we're not actually going to use that approach because it only makes sense in games where you can, well, okay, I need to define exploitative and defensive play. Basically, there is an algorithm that finds the optimal defensive strategy in a game like this, which in rock, paper, scissors is random play. But the instant that you've decided that you want to do better than a purely defensive strategy, you have to think about the concept of exploitation. There are certain games where it is possible to play a perfect defensive strategy that is still in some sense exploitative. There are cases where options generate the same amount of regret in the case where your opponent counters you, but one is strictly better. For instance, we can imagine a very simple game. Let's say that we have the ability to, let's make it even simpler than the simplest games that you ever see. Let's say that I have the ability to give myself $1,000 or give myself no dollars. You have the ability to give yourself $0 and to give yourself $0. You could say that in a sense, there is an exploitative strategy in this game, which is for me to give myself $1,000. Because while there's nothing you can do to make that game worse for me, there's nothing you can do to take my $1,000 away from me, there's a lot of things that I could do to make it worse for myself. I could give myself $0 instead of $1,000. So there are games that allow for a kind of defensive play where effectively the other player cannot do better against you than they would if you were playing any other defensive strategy, but you can do a lot better against them by having fewer regrets. And this is why AI can be really, really good at poker, even though poker is kind of a game where you can, well, okay, I won't get into poker strategy. Poker is complicated, but AI can be good at poker because humans play in a way that is so bad that you can still make money in a purely defensive strategy. So we're actually going to use a different approach because we care about exploitation and we know that all of the strategies that would be found by regret minimization are really boring. There's a reason that the regret minimization tutorials usually use simplified games of poker as a tool to explain them, because poker is actually interesting. Rock, paper, scissors is mostly psychological, so we will just assume that the player doesn't care about the value of their decisions. We won't factor that into our expectations of the player at all. Instead, we will assume that the player is something called a Markov process. It will become obvious to you what a Markov process is as I explain it. So one of the tools used by our adversary is going to be this predictor object. It's going to have quite a few things in it. It has a context size. The context size is the number of game steps that are considered by the predictor. We could say that an agent that assumes that your movement is mostly predicted by literally the thing that previously happened to you, that agent would have a context size of 1. If the agent believes the last 2 things that happened to you are relevant, that agent would have a context size of 2. For instance, it might be assumed that if you found $1,000 on the ground and gave it to charity, an agent with context size 1 would assume that the reason that you gave the money to charity is that you found $1,000 on the ground, because that's the single event that predicts it. An agent with context size 2 might see that you were recently admonished by a priest on the street who told you that you should give more money to charity, and they might conclude that it is the conjunction of the priest and the $1,000 that caused you to give the money to charity. One with context size 3 could observe that you were hypnotized before you saw the priest, and you were told that doing things that priests tell you to is a very good idea. And that person might have a more explanatory model than the person with context size 2 or the person with context size 1. And yet that model would be so specific in the explanations that it uses that it would be less useful. As a result, we allow the context size to be a parameter of our predictor, knowing that more specific predictors can consider a greater number of types of situation, but are less likely to see those situations recur. On the other hand, we'll have predictors with a very low context size that assume that situations generally do recur because those situations are defined in a broad enough way that you can have many situations that are equivalent up to the past few moves. The other thing that will allow the predictor to consider is whether it includes just player moves or just adversary moves. So if I wanted to express the strategy of, for instance, always taking the move that would beat the other player, like if the other player had previously picked scissors, if I would always respond to that on my following move by picking rock, then my strategy could be described by a Markov process of context size 1. That is, if I respond to rock by picking scissors in the next round, if I respond to rock by picking paper in the next round, if I respond to scissors by picking rock, and so on, I'm letting the single move that you made determine my move. On the other hand, if my strategy is to alternate rock, paper, scissors in total ignorance of your move, then a single player move, a Markov process of context size 1, determines what my next move will be, because I'm simply looking at my one previous move and using that. This is a really common formalism. It's used in spam filters. It's used in all kinds of machine learning. It's kind of been superseded by neural networks for a lot of applications because neural networks can learn patterns that Markov models can't. They usually still make what's called the Markov assumption, which is basically that there's an amount of context that you have to look at that determines that chiefly determines your next move. For instance, when you look at a language model that looks at the last 64 characters of text that it generated, it doesn't literally have a recording of what has happened for every possible set of 64 characters of text. What it does is it makes some simplifying assumption about the text. It assumes that the 64 characters of text that it has seen can be mapped to a more stereotypical situation in a differentiable range of situations. So maybe there is a code in four floating point numbers that expresses what the situation was. Maybe this is situation 0.50, -0.50. And that stereotyping operation allows it to use a much smaller data set to make Markov-style predictions about what will come next. Of course, this is a much simpler model. This is one that can be implemented very quickly in Python. And I'm going to be using an inefficient but fairly clever-looking way to implement it because I happen to like the way that the code comes out when you do this. This is a way that calculates the entire probability distribution for the entire history of the game, every step. We'll actually use the choice data type because we happen to have it. We could also use the string data type because, as you'll remember, each choice is just a string. But the choice data type enforces that we're only given choices that are actually on the list. It will make Python complain if the caller does a bad job. We're also going to do some unit conversion. So normally the context size in history items is going to be equal. This is true if the include player moves value is 1 or the include adversary moves value is true, but not both. If they're both true, then we actually get 2 units of information that go into the context from each history item. So we will actually compute that like this. We'll actually use integer division because these numbers should all be integers. We can't really have 0.5 of an item. That doesn't make any sense. Even though, to be clear, this would always be an integer value regardless because we'll happen to construct it that way when we use this in the future of our program. So we're going to add a function, and this function's a little bit cryptic, but I think it'll be possible to understand it just by looking at it. Yes. So we will take the items running from item I to I plus context size. This gets us context size items, and we will build a context string. Then we will, if we only needed half of an item for some reason as part of this, we will chop it up. I think the best way to look at this would be with an example like this. Right. So this is the history that we have. Of course, in practice, we would use rock, paper, scissors. So if we were to take a context size of 1 from this, we might represent it like this. That is raw context. So from there, we might go from raw context to just context. If we're only including player moves, we would get a context of A. If we were only including adversary moves, we'd get a context of B. And if we were including both, we would get a context of AB. From there, we take the actual context size that is desired. We take that many elements right off the end of the list. So for instance, if we imagine that context size was 3 and that we're including both player moves and adversary moves, then the actual number we consider is, oh, hold up a second, this math is wrong. We should round up. Not that it matters for this program. So in this world, we would in fact get 2 items. We would end up building the context string of ABCD. That's if we're including both player and adversary moves, we get both. And then we would helpfully chop it off right down to BCD, which is maybe useful to us. We'll be plucking the context at every possible point. And the reason that we'll be doing that is because we will be training a predictor on that information. So to start with, we have the initial state of our predictor. We'll call this distribution. So what we'll say is that initially we will have observed that each choice was picked 0 times, which is of course true. Like we've seen no picks of any choices at this time. We will then say that we're looking for the distribution of choices. Also, well, actually, we'll use the choice type because we have it. We'll be using the distribution of choices only for situations that match the very last context that can be picked here, the highest value of I that will successfully complete here. So that would be, oh, excuse me. That would be like this. Oh, and we can spell that correctly, and then we'll have happiness. So this is our final context value, and we will now go through all the possible history values. Right. This observation is, of course, the player's move. Oh, there it is. We'll look for it right there at the end of this context window. There we are. That should work okay. I feel like there's an off by 1 error here, but I think there's not. I think this is fine. We will say that if this matches the situation that we're in now, which usually it won't, but sometimes it will. Yeah, the other way, and the way that you'd normally see people code this, is that they would compute this for every possible context sparsely. They would go through all the contexts, and they would start with observations of 0, but every time they see a context for the first time, they would initialize it in a giant table. And the type inside that table would be equivalent to this type inside of distribution here. So the actual type of that would be something like this. And this string would represent context. So if we were to do it that way, then we'd only need to do 1 update every time new context arrives, because, well, we would be able to put the new context into the overall distribution at its proper place. And the distribution updates would be just summed up in the direct way. It would be summed exactly as we do it here, except that we might already have a distribution if this was seen in a previous iteration of the algorithm. Regardless, we'll be doing it this relatively simple way. So we now have a distribution. That distribution doesn't directly tell us what our probabilities are, but we can compute it pretty quickly with math. Apologies, I didn't mean to type a swear, but I typed a swear because apparently spelling is difficult for me. Right. So we now have a distribution. Now, I've engineered a crash for myself, and we'll see the crash in a moment. But first I need to do a little bit more math. I think the I key on my keyboard is fighting me. Does it feel like that to you? Feels like that to me just a little bit. Yes. So we have an adversary here. We actually want the adversary to use this information. And to do that, we're going to need to create a function that wraps the process of predicting. We'll come back to that in a moment. We haven't actually written such a function yet. You'll notice that this is just the same as our distribution type from below, except now we have a list of them. So this is just going to be some math. This basically takes the average of all of them using the mean operation that you're familiar with from school. This is exactly that. We can actually annotate the type to make that clear. Right. So if the tables had a value of, like, let's say that the tables look something like this. Now these would actually be indexed by rock, paper, and scissors. This would produce a merged distribution of, because we would add them all together, we would divide by the total length, and everything is as simple as I have made it sound. What we also want to do is we want to actually generate some tables that represent various parts of the state of the game that we might be curious about. One of the things you'll notice is that there's no weighting here. Like, we treat every item, we treat every distribution as if it has an equal effect on the output. Now, especially if we were building a bot that plays what's called a mixed strategy, which is to say a strategy that is slightly randomized, especially if we were playing a bot like that, we would actually want to we would actually want to weight these in some way that allows stronger predictors or better predictors to be weighted higher than others. As it stands, this has a natural weighting mechanism just because, like, if a Markov model is bad at predicting the player, it's going to kind of converge on a uniform distribution anyway. So we don't need to especially account for that. We'll be using a few specific context window sizes. We can see here that we'll have one that just considers the player's base tendency to make any move. This will just output the overall odds of the player picking any color. This will consider one player move in the past. This will consider one adversary move in the past. This will consider one pair of moves into the past. There's nothing stopping us from adding more of these. It's actually very easy to. These are just the 4 that we'll have. Oh, whoops, apologies. Right. So we've done all that math, and it's pretty exciting. And in a moment, we'll actually make some use of that math. But for now, let's just have it present the predictions made by this ensemble model of hidden Markov models. That would be the pretentious programming way to say it. You shouldn't trust me on that, though. I'm probably using the word slightly wrong. So now we will see what it does when I... Yes! There's the error that I told you there would be. So there's one other simple trick, which is that, like, we actually don't get the uniform distribution out of the system. Let me find it here. I'll show you where the problem is. Well, I'll try to find a problem for you. Right, in predict. We'll zoom out a little bit because this large font size makes me dizzy. So we start with a distribution of 0, 0, 0 across all 3 choices. And its prediction on the very first iteration will therefore, it will have absolutely no clue what you will make. We can actually encode a prior distribution about the player, and what we'll do is that we'll say that if we've never seen a situation before, we assume that the player will act uniformly. This is a trick from math called Laplacian smoothing, and the idea is that, like, maybe I start at something like this. 1 in 3, 1 in 3, 1 in 3. This basically encodes the assumption that we've seen every possible situation one more time than we actually have. If I now play rock, then the odds become 2 in 4, 1 in 4, 1 in 4. So it thinks I like to play rock, but it isn't totally committed to that. However, if I keep playing rock like a lot, you can see that it quickly adapts to the idea that I just play rock a whole lot. Now, the actual constants that you use in Laplacian smoothing can totally vary. You could, for instance, give it a very, very weak bias towards assuming that the player plays rock a lot. So in this world, the actual counts that would be achieved would be 1.1, 0.1, 0.1, which would result in a 12 and 13, 1 and 13, 1 and 13 distribution in the world where I play rock once. And these weights are, of course, something that you can set up artistically according to your own impression of what they should be. Of course, this is tagged as an int, so you do have to pick an integer in this case. But you'll see people use smoothing methods to make the system move gradually from the uniform distribution. In the most extreme case, you could use a value that has like several zeros in front of it. And this is just like the 12 and 13 case, except that there's a whole lot more digits between the 1 and the 3 and the 13. So this would basically immediately make it move out of the uniform distribution. This is a very common technique, again, in spam filters when they realize that they're seeing a situation they've never seen before and they have to attach some weight to it. So now in this world, we should be able to see that the snake has a certain level of prediction for me to make each move. And we'll see when I play rock, its predictions were that I had an even chance of each move at that turn. Now I'll play paper and we'll see. Oh, now hold up a second. Those aren't the predictions. Oh, right. There's more than one model. So having played paper, it slightly weights the idea that I'm more likely to play rock. Most of these models haven't learned anything because, of course, they haven't. We'll actually see it. Let's do it with one simple model that only looks at my current move. And we'll see the exact math that I told you that you'd see. So I'll play rock. And now you can see that it initially had no prediction of what I would play. It was 1 and 3. And now you can see that the distribution moves to the exact distribution that I told you it would have. So we give it the ability to consider each of these things. We, of course, do not weight them in any way. We just hope that the natural tendency of them to reflect uncertainty if they've never seen a situation will cause useless distributions not to affect the ranking. You can sit down and do the math and see that, like, if it just produces a uniform distribution, it's not going to affect the ranking here because it's going to be adding the same amount to every option. It's only when there's a non-uniform distribution does it affect the weighing. So I think this is a pretty good way to combine them. Now, the fact is, of course, that the snake is not going to play any better because the snake strategy is still to pick absolutely randomly from these choices. And isn't that a shame? So what we actually want to do is we want to make the snake predict the expected value of the move that it makes. That is a simple matter of scoring the outcomes of a game. We'll say that, for starters, the score of the outcome, if we did no scoring at all, would be 0. It wouldn't matter. Now we'll consider every possible move. Wow, I cannot type at all today. Right. So this would say, assume that the snake makes every possible move and assume that the player makes every possible move. Then we could say that the table is like this. We'll say that we add 1 if the adversary beats the player. We add -1 if the player beats the adversary. Remember, this is the value of the game for the snake. From the snake's point of view, it's good for the snake to win, even though from the player's point of view, the expected value would be the exact opposite. And we multiply that by the probability that the player actually makes this move. So we'll go back to the single predictor again, and we'll see how that works. We won't actually use the EV yet, but we'll see how it works. So if I play rock, initially it associates, we should make sure that we can see the expected value because that's more useful than simply knowing what it is. Or sorry, simply having it stored. Right. So now we'll play rock. We'll see that initially the snake associates no expected value with any option. If I play rock again, you'll see that it now associates an expected value with paper because there's a 50% chance of me playing rock. Then if it plays paper, there is a 25% chance of me playing a knife. That's -0.25. There's a 25% chance, that's -1 times 0.25 is -0.25. There's a 25% chance of me playing paper, which is 0. There's a 50% chance of me playing rock. So you take the 0.5 that it gets from rock and the -0.25 that it gets from the potential of scissors, and it concludes that this is a great bet. On the other hand, because the exact same math applies, like I have a 50% chance of picking rock, which would be -1 if it picked scissors, and I have a 25% chance of playing paper, which gives it +1 if it plays scissors. So this is how it determines what it thinks the value of its move would be. And there's a couple of strategies that you can use to weight the possibility of a move in a mixed strategy here. I'm not going to bother implementing that because the math is complicated and I only sort of understand it. What we're actually going to do is just figure out, well, okay, what move is predicted to be best? We will then find all of the moves that are tied with that. We know the best score. We don't know the best move. Now we know the best move. And by the way, you'll notice that I'm using an equal sign on a floating point value. It's okay. I got the floating point value just out of this. Floating points don't lose precision unless you do operations on them. So in this case, it's totally fine to use double equals, even though you've probably been told in computer science class that you should never use double equals. So now let's not cheat. we now have a snake that should be playing pretty good rock, paper, scissors. And we can play rock against it. It plays scissors and immediately loses. We'll play rock again. This time it plays paper because it knows that. So I'll just thoughtlessly play scissors. It plays paper, which is great for me. That's good. It'll probably play paper again, so I'll play scissors again. It does play paper again. Terrifying for it. I play scissors. Oh, no, it plays rock now. See, it's figured me out. Well, I better play paper against that. Yes, and it plays rock again. As you can see, wow, it's actually pretty fucking awful. Is it still... Oh, it's only using one predictor. We'll give it back its predictors, and we'll give it another go. There. So now it can look 2 moves behind, and it can also look at my last move, its last move, and it can look at my general tendencies as a player. So I'll play rock, it picks scissors. I'll play rock again. Now it picks paper. Now I'll pick scissors because I bet it'll play paper because I just played rock. There we are. Now I've done that. I think it'll still play paper. Oh, it picks rock. Okay, see, it's learning. There you are. So it picked rock. I better pick paper. There, see, it plays rock again. It's learning. There you are. Now it plays scissors. There you are. See, so if I play paper again, it'll... Oh, see, draw. Perfect. There you are. And now look, we'll play a few rounds against it. I won't think super hard about them. I'll just play in a random way. And apparently I'm really good at this game when I'm not even trying to play super well. Wow, this is a massive failure for the robot. The robot's not doing well at all. We'll switch to... Oh, I'll play scissors. Oh, wow, it really likes scissors now. Apparently I'm really good at rock, paper, scissors. I didn't think I was. We might have to give it a do-over. We'll apparently see that this snake that has a knife is not very dangerous to me. I'm not very worried about it. In fact, I think I might actually be really good at rock, paper, scissors because I'm beating it. And obviously, if I can beat it, I must be great. It's weird because, like, I'm rooting for myself to lose, but not rooting that hard to lose because, of course, I'm not. It seems to be stuck in playing scissors now. Oh, no, it got out of that. Like, one of the problems is that, like, if the first model is playing a large role in deciding what moves it makes, then it will probably play the same move twice consecutively in that world. Now, in theory, if I have a persistent bias, it should still make money from that. The problem is that it does alert me to the... Oh, now it's getting better. See? Okay, that's good. I mean, I'm not really trying to win at this point because when I tried to win, it lost and I felt really bad for it. I'm still winning, to be clear. Like, at this point, we appear to have roughly equal skill. Maybe I'm a little bit better. Maybe I'm a lot better, in fact. Anyway, we can see that this bot is competing with an Austin... Oh, there. Now it's beating me. See? I mean, I'm not even trying at this point. We'll show you how it beats a very naive player. We can see that it beats the all-rock strategy handily right up until I start using scissors. And then I'm pretty advantaged until it... Oh, shit. It figured me out. Yeah, I mean, I shouldn't have given it some games because now it beats me. One of the things that I want to show you, although it's a bit anticlimactic, because as you can see, I'm much better at rock, paper, scissors than this computer, is that if you just look at its valuations, it has a very big problem. We can see, well, we can't see until it's asked to make its move. We can rearrange the code a little bit so that we can cheat with great efficacy. We'll just have it make its choice before I make my choice. So we can see now that it assigns no particular EV to those options, but now, in spite of the fact that it's playing an ostensibly optimized strategy, I can still... Oh wait, I shouldn't have played rock there. We'll try this again. In spite of the fact that it's playing an ostensibly optimized strategy, because it's playing a completely non-random strategy that I know, that I can understand, there is another strategy against it that will consistently beat it. As you can see, in practice, that's not totally true, because playing the exact move that counters it seems to cause it to... Well, it seems to cause it to converge on a defensive strategy that is closer to random. But I will still probably be able to get a lot of points on it whenever it is not playing the defensive strategy that it is approaching. And as you can see, that's absolutely true. I can beat it every time that its move is unambiguous, which is most of the time. The fact that there's a very slim EV margin and yet it always picks the highest EV play is actually a very significant weakness for it, because in theory, it doesn't really matter which of these it plays, and yet I'm 100% capable of knowing which one it will play. Like, if the EV is basically the same for all of these, it should just pick randomly. And that's part of the idea of having a more sophisticated picker approach than the one that I have written right here that simply picks the best choice. You could decide how much EV it wants to throw away. That's an option. There's algorithms that do this that I fully admit that I don't really understand because it's been ages since I've implemented them, but maybe I'll come back to them. As it stands, this is the approach that we'll use, and as you can see, the snake is just absolutely baffled. This is, of course, much higher than the win rate that I had when I was just playing against it according to my intuitions, which was still a pretty high win rate, just to be clear. Anyway, I think that I've satisfactorily explained that this snake, which is my enemy, can in fact be beaten, but it's a formidable opponent against truly bad players, which is to say it's not an especially formidable opponent. You can, of course, find the code for this along with all the other code on my Git repository, which I will be linking. There's one other thing that I want to exhort you to do, which is that my most recent video, the video where I make malware using 4 different programming languages, that's one of the best things I've ever made. So you should absolutely just click through to that because it's fantastic and it's not getting enough attention because it's a 2-hour video. It's definitely the hardest programming project I've ever done from this channel, and working on it made me incredibly happy, but seeing attention for it would make me even happier. I hope you have a restful one, and remember that this snake truly is very dangerous and represents very many metaphorical things.